Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 2. The Power Method. The power method is an iterative numerical algorithm to find simultaneously the dominant eigenvalue, largest eigenvalue in magnitude, and its associated eigenvector of a matrix. Computing the dominant eigenvalue is of primary interest in many physical problems, where approximating spectral properties of matrices is required. For instance, dominant eigenvalues help determine the natural frequencies of mechanical structures of bridges, aircrafts, etc. The power method is a widely used iterative method for finding solely the dominant eigenvalue of any non-singular matrix, whether symmetrical or not. Consider a non-singular n by n matrix A with n eigenvalues, lambda 1 being the largest absolute eigenvalue, and linearly independent associated eigenvectors, satisfying the eigenvalue problem. An arbitrary initial vector x can be constructed as a linear combination of n eigenvectors. Left multiplying the initial vector x by the matrix A yields. Invoking Ax equals lambda x, we obtain. Left multiplying both sides of the prior expression with matrix A and invoking the Ax equals lambda x relationship, again, yields. A sequence of successive multiplications can be expressed as follows. Factoring out lambda, 1 to the p from the right-hand side yields. For lambda 1 being the largest eigenvalue in magnitude and p going to infinity, we may write it follows that. Note that if C1 equals 0, then the above expression would yield the next eigenvector with a non-zero coefficient. For non-zero C1, the scaled sequence converges to the eigenvector of the dominant eigenvalue. In practice, the dominant eigenvalue can be obtained by comparing the corresponding elements of two consecutive vectors. For a large enough p, we have the following. Where xi to the p denotes the ith component of the associated vector at pth iteration step. The convergence is observed to be at least of first order with the ratio at most lambda 2 over lambda 1 to the p. Then the convergence rate may be defined as the natural logarithm of lambda 2 over lambda 1. The power method with scaling is a refinement of the standard power method used to find the dominant eigenvalue and associated eigenvector of a matrix A. The scaling, or normalizing, improves convergence behavior and helps avoid overflow or underflow in floating point computations during power iterations, thereby improving numerical stability. The scaling of x is based on the largest component of the estimated eigenvector, i.e., the infinity norm, as follows. Next, comparing the scaled equation to Ax equals lambda x, the largest component of x at the pth iteration converges to the dominant eigenvalue as p goes to infinity. A convergence criterion can be based on either the relative or absolute error of the largest eigenvalue, or the any norm of the difference of two consecutive eigenvectors. Another common algorithm, called the Rayleigh quotient, is based on a single criterion. The procedure starts with an initial arbitrary non-zero vector, and then the dominant eigenvalue is estimated in each iteration by where p denotes the iteration step and u comma v in parenthesis the inner product. The convergence status is checked at the end of each iteration, and the iteration procedure is terminated when the stopping criterion is met. The number of iterations required to converge the dominant eigenvalue within a predetermined tolerance depends on the initial guess. The method may not always yield the dominant eigenvalue for every matrix. The convergence strongly depends on how well the two largest eigenvalues, lambda1 and lambda2, are separated. That is, lambda1 is much larger in magnitude. In this respect, the dominance ratio lambda2 over lambda1 being smaller than 1 is important in assessing how quickly lambda1 overwhelms other terms. If lambda2 over lambda1 is less than 1 and lambda1 dominates other terms very quickly, the convergence is fast. Otherwise, it is slow. If the largest two eigenvalues coincide, the method may or may not converge after a large number of iterations. If two eigenvalues are equal in magnitude but have opposite signs, the dominant eigenvalue can be estimated by applying the power method to a squared, where the eigenvalues of a squared satisfy are equal to the eigenvalues squared of the matrix A. However, if the initial guess corresponds to any one of the non-dominant eigenvalues of A, then the method fails due to converging to the wrong eigenvalue. The advantages of the power method are: the method is simple and easy to implement. Each iteration requires only a single matrix vector product, AX, which greatly reduces the computational effort, especially when A is very large. It gives, when it converges, the largest magnitude eigenvalue and its associated eigenvector simultaneously. Rayleigh quotient version, which generally converges faster, is effective for symmetric matrices. The disadvantages of the method are: it only gives the dominant eigenvalue and its associated eigenvector. Its convergence rate depends on the dominance ratio. Its convergence is very slow when the two largest eigenvalues in magnitude are close to each other in magnitude. It is sensitive to the initial guess and matrix condition number. It converges to the wrong eigenpair if an initial guess coincides with an eigenvector other than its dominant eigenvalue of A. Let us consider the following matrix, which is symmetrical. We would like to determine the dominant eigenvalue using the power method with both scaling and Rayleigh quotient. We will use 0.5 times 10 to the minus 6 as the stopping criterion and a vector of 1s as an initial vector to start the power iteration. We begin by calculating the product of matrix A and the initial x vector, which yields: the largest value in the resulting vector is 24. Normalizing the vector with the largest element gives the next eigenvector estimate, x1. Next, we multiply the matrix A with the normalized eigenvector estimate x1, which gives. Likewise, we find the largest element in the product vector, which is 26.25. Normalizing it with this value gives x2. We always normalize the resulting vector by its largest value in magnitude. This prevents the numbers from growing too large or becomes too small, and stabilizes the process. We repeat this process for the third, fourth, and subsequent iteration steps by multiplying the currently computed vector by matrix A, then find the largest value, and scale the current vector estimate until the vector no longer changes by much. The iteration process results in 6 decimal place accurate estimates in 51 iterations. we find the dominant eigenvalue to be 33, an eigenvector as 110-1. The Rayleigh quotient method, like the scaling method, multiplies an eigenvector estimate by the matrix. However, instead of seeking the largest value in the vector, the method uses a more accurate formula to estimate the eigenvalue. We let W be the product of A and the initial vector x. We then compute the inner products of x0 and W, as well as the inner product of x0 by itself. The eigenvalue is estimated by taking the ratio of the two quantities as follows, which yields 8.25. We then normalize the vector with its maximum magnitude to find the current estimate, x1. Using the new estimate, we compute the vector W, which is the product A and x1. Next, we calculate the inner product of x1 and W, and the inner product of x1 by itself. Then, we obtain the current eigenvalue estimate as follows, which yields 27.082. We repeat this process for the third, fourth, and subsequent steps. The eigenvalue estimates improve significantly at each step. This iterative process continues until the difference between the eigenvalue estimates and the norm of the displacement vector are less than epsilon. The iteration process results in 6 decimal place accurate estimates in 45 iterations. This method converges faster with a quadratic rate of convergence, especially near the true eigenvalue. With this note, we conclude this video lecture. That is all for now. See you next time with another topic. Bye.